Welcome students to this next session on industrial metallurgy, and we are going to start with a very interesting topic called the iron carbon systems. In this particular session, these are the contents that we'll cover. So let us start. You see, pure iron is a silvery whitish metal and is the most important industrially used metal because it is the primary constituent of some of the most popularly, most importantly used engineering alloys in the industry. And these alloys of iron are called steels and cast irons. Now, iron in its almost pure form is very soft, is very weak, has very low strength, and importantly, it's very expensive to produce iron in its pure form. Uh, in the next slide, maybe I'll show you that what are some of the important commercially used forms of pure iron which different companies have produced. Armco was a pioneer company in this field which produced pure iron for the first time, right? But what makes iron so important, one of the reasons behind this is the allotropy shown by pure iron. There are about 15 metals known to us which show this characteristic or phenomenon called allotropy or called polymorphism. I'll define this for you. Allotropy is defined as the ability of a material system to exist in more than one crystalline forms depending upon the external conditions of temperature or pressure or both. And iron is amongst those metals which are capable of showing this phenomenon. So let's look at this cooling curve of pure iron. Now, if you look at the cooling curve of pure iron at room temperature conditions, if we have maintained pressure fixed at 1 atmospheric pressure, iron has got BCC crystal structure. So if you take a pure iron sample under atmospheric conditions, under room temperature conditions, you will see throughout iron there exists only one region, one phase called the alpha phase, which is BCC in crystal form. And right from 0 till 910 degrees centigrade, this phase will continue to exist in iron, and as such iron is called alpha iron. The iron from 0 till 910 which contains BCC phase, alpha phase in it, is called alpha iron. Yes, there is some characteristic change which comes over here at 768. At 768 happens to be the Curie temperature of iron, where iron changes from ferromagnetic character to paramagnetic character, becomes from magnetic to non-magnetic. So this iron which exists between 768 to 910 is again BCC crystal iron, crystal form only, but it represents a significant physical change, that it has changed now to non-magnetic character. But magnetism is a physical property and it's not considered as a phase change if magnetic character of a material changes. So right from 0 till 910 we have only one phase in iron called the alpha phase, and the iron as such is called alpha iron. Yes, this alpha iron at 768 changes its magnetic characteristic to being non-magnetic or paramagnetic, and students, for some period of time this non-magnetic alpha iron, this non-magnetic BCC iron which exists in the range 768 to 910 by the Japanese were also referred to as beta iron. But nowadays this is not used because that creates a confusion. As you start saying beta iron, it appears as if some other phase has appeared. No, phase is the same from 0 till 910. It's only that that phase has gone a significant change in a physical property, that is magnetic character, and becomes non-magnetic beyond this, right? Okay, so then as the iron reaches 910, it starts changing its crystal structure from BCC to FCC, and we say that a new phase appears to begins to appear in iron. And after some time, see, this represents the time period that would be taken for transition of BCC crystal structure to FCC crystal structure, or in other words, this is the time which would be taken for transformation of BCC alpha iron into gamma iron. But no sooner the stipulated period of time is over, you have again one phase in your system, and that is called the FCC iron, or the gamma phase, and the iron as such is called the gamma iron. But if you look into the microstructure of pure iron at 910 degrees centigrade, and this much of time period has not elapsed, that means you will be able to see two phases in iron. You will have already existing alpha iron, which is getting converted into gamma iron, and you will also see the freshly formed gamma iron. Okay, so from 910 till 1394, we have one phase in iron. That phase is having FCC crystal structure. The phase name is given gamma phase, and so iron between 910 to 1410 is called gamma iron. Then at 1410, this FCC crystal structure again starts getting transformed to BCC crystal structure. So again, we have a phase change at 1394, not 1410, sorry, 1394. This FCC crystal structure starts transforming to BCC crystal structure. But students, this BCC iron that you now see between 1394 and 1539, and the one you saw below 910, both are BCC. But mind it, because here the iron is at a significantly higher temperature, the lattice dimensions are different. You know that one phase differs from another phase either in terms of chemical composition or physical state or crystal structure or lattice dimensions. So this phase, which we'll refer now as delta iron, and this phase which we were referring as gamma iron, in three of the things, chemical composition, physical state, and crystal structure, they are the same. But the fourth characteristic, that is lattice dimensions, because this has got a significantly larger lattice dimensions, this is a different phase, and it would show different mechanical properties as compared to alpha phase. And so these are two different phases. So this is alpha iron, but in this range we have delta iron. Now students, as you reach 1539, which happens to be the melting point of pure iron, iron will completely melt, and beyond this temperature you'll have only one phase in iron, that would be liquid iron or liquid phase. And beyond 3000 degrees centigrade, you will have what is called gaseous iron or vapor iron, whatsoever you call it. So iron show whatsoever changes iron shows during heating, the same it shows during cooling. And if a material shows only either during heating or during cooling some changes, then it's referred to as polymorphism. If the changes are reversible, as are in the case of iron, then the property is called allotropy. So iron is an allotropic element, which makes it very versatile, and it goes on to make some very important commercial alloys, which we call as steels and cast irons. So in the purest state, though I said that in the pure state iron does not find much applications, it's just used in as a base for porcelain enamel. It is used in some magnetic circuits because of its good magnetic characteristics. But otherwise, pure iron is a very feeble type of an engineering material, which needs alloying to improve upon its properties. But still, some of the popularly available commercial forms of pure iron have been listed in this table for you. One is the Armco ingot iron, which is produced by this company called Armco. Then we have another form called the carbonyl iron, the electrolytic iron, the hydrogen purified iron. Then we have this wrought iron. Wrought iron is essentially not pure iron, but it's a mechanical mixture of iron and silicate slag. Why we have listed it over here? Because before, mild steel was known as a material and was used in engineering applications. It's wrought iron which was used for most of the purposes of construction, etc. And so we thought that we should be mentioning it over here. Then students, need of iron carbon system. See, that need has already been stated, that pure iron as such is not a useful commercial alloy and it must be alloyed. Now, need of iron carbon system is that see, it was observed through research that carbon is the most important alloying element which affects the allotropy, the crystal structure and the properties of pure iron. And when we mix a little bit of carbon to iron, it dramatically, drastically, significantly improves upon the mechanical properties of pure iron, and thus that justified the need of having iron carbon systems. Now, we are studying metallurgy at the moment, and if we are interested in understanding any system, for example, if we are interested in understanding the iron carbon material system, the best way as a metallurgist to understand any material system is through drawing its equilibrium diagram. And students, when we draw the equilibrium diagram for iron and carbon, the equilibrium diagram is called iron carbide equilibrium diagram. Now you must be wondering that why not iron carbon equilibrium diagram, why iron carbide equilibrium diagram. Now, to understand that, please think in the practical terms that, see, if I have to form iron carbon system, I have to start mixing carbon into iron, starting from 0% carbon, 0.01 percentage carbon, then I'll keep on increasing. And so the first extreme would be that I start with 100% iron and I have 0% carbon, and then the composition would be increased. I'll have 0.01 percentage carbon and 99.99 percentage of iron, and I'll keep on increasing the carbon amount. But you see, I will uh, I, I will make a diagram, or I will list 100% iron on one side and 100% carbon on the other side only if a particular system exists. Now, it has been known that carbon, the maximum amount of carbon which in any form, in the form of a solid solution or in the form of an intermediate phase, the maximum amount of carbon that can go into iron in the solid state is 6.67 percentage by weight. If you try to put more than 6.67 percentage by weight of carbon into carbon will come out in the free form. So students, when you have started with 0% carbon and 100% iron, the maximum you can go up to is 6.67 percentage carbon and remaining 99.33 percentage of iron. There is no system which exists beyond this. So, and when there is exactly 6.67 percentage of carbon and 93.33 percentage of iron, it forms a transitional phase, an intermediate phase called iron carbide, or which popularly is also called cementite. So when we draw the equilibrium diagram of iron carbon system, what are the two? See, when I say copper nickel system, I have pure nickel on one side, I have pure copper on the other side. When I say lead tin system, I have pure lead on one side, I have 100% tin or pure tin on the other side. In case of iron carbon system, it's not possible. On the one hand, I have pure iron, but on the other hand, I have pure iron carbide or iron cementite, which is 6.67 carbon, 93.33 percentage of iron. So the equilibrium diagram for iron carbon system is iron carbide equilibrium diagram, because when I say lead tin, I'm taking the names who form the X's the two axes of the equilibrium diagram. When I say copper nickel, I know the left axis is pure copper, the right axis is pure nickel. Similarly, for iron carbon system, the left axis is pure iron, the right axis is pure cementite. So the diagram would be called iron carbide equilibrium diagram or iron cementite equilibrium diagram. I hope you have understood this basic introduction to the iron carbon system, and in the next session we'll draw a very important diagram, the most important, I think, from a physical metallurgy viewpoint, that's called the iron cementite equilibrium diagram or the iron carbide equilibrium diagram. Students, thanks for watching.